Alrighty, y'all. Today we're taking a look at how to dot product. In this video, I'm just going to take a closer look at what a dot product is and generally just how we've been applying it. So dot product, it's also called a scalar product because really what we're doing is we're taking any two vectors and when we dot them together, the output is a scalar. So this is the application we've been using thus far is for our work energy theorem, where we have our force vector and we dot it with our displacement vector, and the output is energy. And this makes sense because energy is a scalar, right? So our first way that we're going to be taking the dot product, I'm just going to be dotting these two vectors. We're just going to be doing A dot B. And the first way we're going to do, we can do the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them. Okay? So we have magnitude of one is 8, magnitude of the other is 5, and the angle between is 30. So for this one, our dot product is going to be 8 times 5 times the cosine of 30. Okay? And punching that into a calculator, it spits out approximately 34.64101615. So this is our first dot product of these two vectors. Now we're going to go on to another way to take a dot product. We see there's a mess of an angle here. That's because I was trying to make this problem work a certain way. Really, I just wanted to make sure that this was labeled as a 3, 4, 5 triangle, just to make my life easier. So this way, we're going to be looking at A times the parallel projection of B. So pretty much all this means is I'm taking A and I'm only looking in this direction. I'm only looking in the direction of A. So I'm going to take the chunk of B, I'm going to take the component of B that's parallel with A and multiply that with A to get the dot product, right? So for this one, I'm just going to go perpendicular to A. Right, I'm just going, that's not my marker. I'm going perpendicular to A. I'm going up to B, to the tip of B. It's kind of making this triangle, right? If it wasn't a perfect 30, 60, 90. Up here we had a 30, 60, 90. If it wasn't a perfect 3, 4, 5 triangle that I designed it to be, right? We could do trig to find our x component of this triangle, because that's really what we're looking for right now. Since A is aligned with x, we're going to get our x component of our B vector, and then we multiply that with A. That gives us our dot product. But since I lined it up perfectly, I'm just going to count the squares. You have 1, 2, 3, 4. Right, so our B parallel is 4. So now if I do my dot product of A dot B, that's going to be my A, which was 8, times my parallel portion of B, which was this 4. So for this one, the dot product is just 8 times 4, which is 32. Would have been bad if I got that wrong. And it's close to the one up here, right? The angles are very similar and the dimensions are kind of the same. They're not supposed to be the same because obviously it's different angles. I'm just using these as two separate examples. Now let's look at another way to take a dot product. Right now we're going to get A parallel to B and multiply it with the magnitude of B. This one I drew it to scale, so this just means I can count the squares. So I want to find the portion of A that's parallel to B. This one's kind of tricky because I'm looking at this and B isn't lined up with my y-axis. It's not lined up with my x-axis. But we know a strategy for that. We have learned to tilt our axes, right? So if I just decided to say that this is my y-axis and this is my x, now B is along this axis. I just get the components of A, and it works. So what I'm going to do to make my life a little easier, instead of tilting my axes, I'm going to tilt my vectors. I'm just going to tilt my vectors without changing the size too much, as best I can. I'm going to put that so that B is lined up. I've just all I've done is tilted my frame of reference. I haven't changed the magnitude. I haven't changed the angle between. So I haven't changed my dot product. So now we just figure out our dot product from here, our parallel portion of A. So same thing, since B is going along the y-axis, it's not perfect. We're going to estimate this to be roughly around 2, right? So we just needed our y component of A, which if we needed to do trig, we could. Obviously, we have angles and stuff that we would, and such that we would know, and we could use trig because if we had the magnitude of A, I don't right now because it's a little bit off, but we're gonna estimate and call it to scale. So that means B is 1, 2, 3, 4, 5. A is in the parallel direction. Oh, I should switch to my red pen. This is my A parallel, which is, we're gonna call it roughly 2, which means that our dot product for these two vectors is 10. Well, that's the answer. 5 times 2, which is our 10. Right? And so far, this has been making sense, right? Because our parallel direction of this, if we're looking, they're kind of going in the same general almost direction, so it gave us a positive answer. This one, they're also just going in the same general direction, gave us a positive answer. Same thing here, they're going kind of in the same direction, so now that's a positive answer, which is what we were saying with our work. When our force is going the same-ish direction as our displacement, that's when we have positive work being done. So now we're going to take a look. Oh, this one's also to scale. That makes it easier for me. So now we're going to look at, there's another way to take a dot product. Right? So generally, by definition, a dot product, I'm doing A dot B. We break it up into components, and we do AX, BX, plus AY, BY. Right? I take each component in the direction, multiply them with the other component in that direction. Then I do the same for each direction and sum them all together. So that's how I'm going to do this one. Right? So A, I'm going to break into X and Y components. And I said this one's to scale, so this one's just designed to be counting the squares. So for this one, my AX is 2. My AY is 3. Now I'm going to do the same for my B vector going down this way. This is going to be BY equals -4, right? Because we still have to keep track of the fact that it's going down. And this way, BX equals 1, 2, 3, 4, 5, 6, 6. Oh goodness, can't count tonight. All right, so now I have all my components, all my X and Y components. Again, if I wasn't just counting squares, I would have thetas. I would be doing trig with like my sine and cosine to get my different side lengths. But since I made it easy for myself, I just get to do that. So now we're going to do our dot product, AX, BX. So AX is 2, and our BX was 6. And we add that with our AY, BY. So AY was 3. Oh, that was gross. And our BY is -4. Right. So now we add these together. It's going to be 12 plus a -12. And oh, would you look at that? Our dot product is 0. How could this happen? We may be asking. It's almost like I designed the problem to do this. So just getting rid of these markings real quick. So what that tells us is that these two vectors are perpendicular, right? If I did what I said before, right, and I tilted my axes so that they lined up in such a way, so I take this and tilt it, You can see very clearly as it lines up with the grid paper that they're perpendicular. B doesn't have a component in the A direction. So if I now look at it like this and I said AX BX times AY BY, my AY equals magnitude of this, which is going to be 1, 2, 3.5, 3.5, sure. And my AX equals 0, right, because we're not going in the X direction. Now my BY equals 0, because we're not going in the Y direction. And my BX equals 1, 2, 3, 4, 5, 6, 7. Wonderful. I mean, I can calculate like actual magnitudes and stuff based off of the squares I counted before, but I'm not going to do that. Now, if I multiply out my dot product with the tilted axes, I get my AX, which is 0, times my BX, which was 7, plus my AY, which was 3.5, times my BY, which was 0. And here, this side cancels because multiply by 0, and that's both of our X and Y sides will cancel out. We get a 0 dot product. It also works if we think of our AB cosine theta, right? Since this is a 90-degree angle, it's a right angle, we're taking cosine of 90. It doesn't matter how long A or B are. Our cosine of 90, if that's the angle between them, cosine of 90 is always going to equal, cosine of 90 is always going to equal 0. It doesn't matter what this is because we're multiplying it by 0, and that gives us our 0 dot product. So that means that this force does not do any work if the displacement is like this. Or this force doesn't do any work if this is our displacement. Again, it doesn't matter, we're just dotting them together. It doesn't matter the order, but this is what we're thinking about. This is the application that we're looking at, because whenever we do our dot product, right, thus far our application has been with the work energy theorem. So like I said, they're going in the similar direction, positive, but this, they're perpendicular, so our work is 0. Now how about if they're not going in the same direction, right? This is a 120, this angle looks weird and I don't know how to do it and it's bad and I don't know. Either way, it's fine. Sydney says it's fine, that means it's fine. I believe in all of you. Even if the angle is larger than 90 degrees, we can still use the same methods that we have been. We can do AB cosine angle between them. And this time the angle between is just 120. It just happens to be larger than 90 degrees. And it works, right? If we recall our unit circle, I know we all love the unit circle. If I am looking at, right, this is very well drawn by Sydney. I should have lined it up with the grid lines. Give me a second. I'll line it up with the grid lines so it doesn't look as gross. There, it's a little better. No, it needs to be, forgive me as I forget how to do my job. There we go. All right, so now it's sufficiently lined up. I can draw some axes on this like this. And now we have like our 0 and our 2 pi. Okay, this is, I'll do it in degrees. 0 and 360 degrees. And then as we go around this way. So it's 90, 180, 180, and 270. Okay. So if starting from this axis, I go and my angle is less than 90. Right? My cosine is my x direction. So here's my cosine because the angle's from the horizontal here. Cosine of this theta, I drop it down here. Here's my x. From my origin, my x is going to be positive. So if theta is between 0 and 90, my x is positive. But then, if we look at when theta is bigger than that, like our 120 over here, cosine of this suddenly, drop this down to the axis. Here's my 120. Drop it down to the axis. Now here's my x. X is to the left of the origin. That means we have a negative for our cosine, right? Which makes sense. This is going kind of away from, the vectors are going in almost opposite directions of each other. If I did it with my parallel, if I thought about like which direction is parallel, I'm just getting that out of the way, right? I have my this way direction, and I'm going to get the parallel component of this. The way it falls on this line, right? I just extend this line out, and the same thing, I go perpendicular to it here, and to the tip of the other vector. Here's my parallel component of my second vector, magnitude of 3, but they're going in opposite directions. And we said when they're pointing in opposite directions, that's when we have negative work. So for this one, right, our dot product's going to be 8 times 3. 8? Oh, I doubled the, it's not entirely to scale, it's double to scale, because this is 5, this is 8, or this is 5, this is 4, so it's double. So it's going to be 8 times 6, really, because just doubling the lengths. But, and 8 times 6 is, oh my goodness, I gave myself tricky math, I can never remember. This is 48. So that's our dot product of these two vectors. And if I did it out with 120, it would spit out the same answer. And if I worked it out by getting the parallel component to this, it would give me the same answer. Well, let's do that one real quick too. So I rotate it because I want this on an axis, right? And we try to line it up as best we can. All right, this is going to be 10 times our parallel component here. That to me looks a bit like 2.4. So 2.4 squares, if I double that, that becomes, so if this is 2.4 there, but we double it because I changed the scale on myself to make things fun, 4.8. I kind of, obviously it's close and it looks close, and I actually didn't scale very much, and I'm kind of proud of that. But that's when we do, right, we get our 10 times our 4.8, and again, they're going in opposite directions, so that's not my pointer. They're going in opposite directions, so it's going to be negative. Right? Sorry, this is negative 48. And again, so I can say 10 times 4.8, and it's negative, so I can say it's negative 48. And the reason it's negative, right, again, because we can say that 10 is pointing in a negative direction. I just didn't set, since I was tilting my axes all over the place, I didn't set a direction that was positive and a direction that was negative, but that would have accounted for the sign of my dot product on its own, right? Because if I say this is negative, 10's pointing negative, 4.8 isn't, that puts the negative in here. If I say this is negative, 4.8 is negative, 10 is positive, puts the negative in here, and they both give out a negative answer. All right. Well, I hope you found this video at least a little bit helpful. I know people could just needed a review on some dot product stuff. Let me know if you have any more questions about dot products or anything else that you want me to try to explain, and I'll do my best to try to explain it, because I guess Sydney explains stuff.